That's down.
Let go at the back. Let John balance it and feel it. Now let go. Now put up the other way.
That pitches.
Yeah, apart from that lump in the middle, they get flat together there.
Yes, I think that's as near as we'll get her.
Just tip that round a bit more on that tip.
Yes.
Do you lower the right hand tip slightly?
The tail at all? Push it down. Oh, I see. That's great.
Rhossili Cliffs, South Wales, August the 12th, 1975. Dr. George Whitfield, an electronics engineer, and Cherrie Bramwell, an expert in prehistoric flying animals. Today, 7 years' research ends. 70 million years after the last pterodactyl soared over these cliffs, the largest flying creature ever known is to fly again.
I feel it bears a strong resemblance to the Apollo launch to the moon. Very strong. It just reminds me of it all the time. All we've got now is a countdown.
Well, I'll count for you, Cherrie, if you like. I can get to 10.
And how are you feeling in yourself?
Oh, I just feel it's just got to go. I mean, it's just got to go. Either it goes or I go.
After all the thunders we've had, I think I know how Brunel felt when he couldn't launch the Great Western.
The work which led up to the launching began here in the Natural History Museum. These skeletons are up to 150 million years old. It's difficult to imagine their distant world. But for Cherrie Bramwell, dinosaurs might still rule the Earth. She recreates every detail of their daily lives in her imagination.
I think of all sorts of things. I pick up a tooth and I think, good Lord, that's a sharp tooth. And I think, I wonder what fish it dug in. And I think, fancy seeing the enamel after 80 million years. I think, I wonder if this poor particular pterodactyl ever had toothache, and what would you do if you did?
At Reading University, Cherrie was given the routine task of classifying and sorting pterodactyl bones into separate species. This is how fossils have been studied for over 100 years. It was dull and repetitious work. Her interest lay increasingly in building up a picture of how Pteranodon, largest of the pterodactyls, lived and flew. The work of classification ground to a halt.
When I don't like something, I go away and do something else. And what I did was sit there and I'd gaze out of the window and imagine Pteranodon flying by. And there's a lot of very nice modern buildings in the university, and I used to look for hanging places for pteranodons and see how many I could arrange along particular buildings, things like that.
And what happened to change all this?
Oh, well, I met George. That was my salvation, definitely, because I got out of this sort of awful, oppressive, dull work in an equally awful, oppressive, dull department, and found George and had a wonderful time from then on. We really got down to pterodactyls. We really did proper research after that. Let's keep the nose up.
The bones of Pteranodon were first unearthed in 1876. Since then, discoveries around the world built up a picture of a huge winged creature that survived on Earth for 100 million years, 50 times as long as man.
Yeah, got it.
Forward a little.
Forward.
And lower away.
Gently down.
Yet still no one could answer the most fundamental question of all. How did it fly around the ledges and cliff tops where it lived? Pteranodon had wings 27 feet across, twice as wide as the largest bird flying today. The problem was its bones were as thin as drinking straws. How had it the strength to fly or survive even a gentle landing? It seemed obvious to Cherrie that an engineer would know more about this than a zoologist. She asked George Whitfield, whose hobby is gliding.
Well, the starting point certainly was calculating the flying speed, because that removed a lot of the difficulties of previous understanding. People had thought that with such fragile bones and such a very large animal, it couldn't land without breaking. And obviously, the animal existed, so it did land without breaking, and the difficulties were all in the minds of paleontologists. When we worked out the flying speed, it was obvious that it landed very slowly. and landing very slowly. The loads are very light. There's no reason why it should do any damage.
What kind of a calculation is this to do? How did you
Oh,
do it?
it's very simple calculation, familiar to anyone in aviation. The speed at which an aircraft has to fly depends on its weight and the area of its wings. And as I say, any pilot could work this one out.
Cherrie, what was your reaction to these kind of discoveries?
Well, I just thought it was a marvellous thing to actually use mathematics to find out the true reasons rather than just a mass of supposition. Because through a physics approach, you can say either a thing could function or it couldn't, or it is or it isn't. You narrow down the range of possibilities and emerge from that with a clearer picture of Pteranodon as a living, flying pterodactyl.
Well, now, in order to find out all these things, you obviously needed to locate the evidence. How did you do that and where?
Well, you locate the evidence by going first to the fossils, to the bones.
So began 3 years' detective work in the museums of Oxford, Cambridge and London.
We can get the thickness from these, I think.
Oh, good.
It's a nice humerus.
Drawers and cabinets, some unopened for 60 years, began to yield dusty evidence. Clues whose usefulness to zoologists had been exhausted, but were invaluable to an engineer.
I'm trying to understand the animal from the point of view of an engineer, which means I'm treating the creature as if he were an aircraft. I'm stressing him to see if he's strong enough. I'm doing performance calculations to see what he could and what he could not do.
A critical factor with any aircraft is the strength of the wing. Previously, no one could understand why the paper-thin wing bones had not snapped under the stress of flying. Tests revealed that just enough material was concentrated at the corners of the triangular sections to give an exceptional combination of strength and lightness. Pteranodon had anticipated the box girder by 100 million years.
The point is that the animal's bones are extremely clever. They're as thin as drinking straws, and the material has been put in just the right places to give the maximum possible strength for this given weight. And we couldn't hope to match this in an engineering structure.
See the spike on his thumb over there that he's supposed to use for defence? They had it on their nose originally when they reconstructed them.
George quickly caught Cherrie's enthusiasm.
Ulna, 24.5.
Like every good detective story, each solution raised a new problem. The performance of a wing depends on shape as well as strength. Previous calculations of the angles of the joints and therefore the shape of the wing had been largely guesswork. This was to be the problem.
The lengths came from the larger bones, which you can see in any museum, but the angles came from this sort of collection.
This fragmented jumble of fossils was raked over for bones from similar joints which could be stuck together with plasticine. Straws were added to extend the axis and so draw out an accurate plan of the wing. Pteranodon was taking its true shape for the first time for 70 million years.
And that's the next joint. It's rather like reconstructing a crashed aircraft from the pieces. To set a wing like this, we need a set of bones for every joint. We were lucky. We found one set for every joint, and that's about as much as we did find. This allows you to convert the paleontologist's reconstruction, with all the bones just sort of strung end to end, into a proper engineering reconstruction with all the angles right. This allows one to treat the thing as an aircraft, see how it must have worked, and really get a feel for how the living animal must have flown, and how it must have lived.
Yes, it in fact got the bones off the table and back into the air.
Yes, that's it.
Oh, good stall there,
Yes.
George.
Having determined the wing shape, Cherrie and George realised that Pteranodon combined a huge wing area with minimum weight. Instead of the crude, clumsy creature from prehistory, the Pteranodon had turned out to be the most sophisticated glider ever. This success meant that Cherrie's attitude to analysing fossils would never be the same again.
Oh, it was a completely different attitude, because before I was just measuring them to classify them, which is a technical job, just requiring a bit of expertise. But afterwards, working with George, every measurement was significant in building up a picture of Pteranodon, how it flew, how it worked, its wings, its joints, its flapping, everything. And that was a truly scientific job, requiring sort of imagination and creativity.
Cherrie came to see me and asked, how does it work? This opened up a completely new field because the whole of engineering and aerodynamics could be brought in. And generally, this is the way to make big advances, to ask the right question, which of course changes with time, and brings in a body of new knowledge which has been building up somewhere else to an old problem.
Researches in the museums began to take practical shape. George built a small balsa wood model to show the degree of movement of the joints. This proved that the legs pointed backwards and the wings folded when the animal was at rest, just like a bat. So Cherrie bought a fruit bat. Comparison with the membrane-winged and upside-down way of life bore out that Pteranodon's legs were not strong enough for an undercarriage. It took off and landed like a bat and hung itself from the edge of cliffs before takeoff. The last great unsolved problem was the crest on its head.
The most obvious feature is this enormous crest, which in an animal which has obviously saved weight by all possible means, seems a silly thing to put on. Again, the biologists didn't really understand what the crest was for, but to an engineer it looked obvious that this was an aerodynamic balance balancing the beak, that when the head looks sideways, the wind blowing on the beak will tend to blow it round. But of course, as the head goes out one side, so the crest goes out the other, and the wind blowing on the crest balances the wind on the beak. And when you do the sums on this, you find that in fact, because he's got a crest, he needs lighter muscles in his neck, and the saving in neck muscles is in fact greater than the weight of the crest.
The pieces of this story were fitting together like a three-dimensional jigsaw. Were they elated by their success?
I don't think I've had a moment of greatest elation. The original research went like a good detective story, where one kept finding new clues, old clues, 60-year-old clues with all the dust on them, but seeing the significance of them. And it was a steady increase in understanding, a sort of continuous elation.
Whee! Boom! Oh dear.
Done again.
Differences in scientific background are matched by equal differences of character. In contrast to Cherrie's intuitive approach, George Whitfield is a man of orthodox method. He has a much greater attention to detail than Cherrie. Less typically, he has a boyish enthusiasm for everything he does.
Out! William in!
Married with 3 children, he still prefers the orderly world of science to the rough and tumble of people and their problems.
Ready? I think you're right. I think I'm not very good with people. I'm much better with things. I don't know whether this comes from my interest or whether my interest follows it. Certainly I tend to be more interested in things than in people. Loud cry if you've lost it, Jenny, so that we know.
Cherrie Bramwell left school at 16. She studied at night for A-levels while working by day as a lab assistant. She then studied in her own time to graduate eventually in zoology. This rather checkered career seems to have developed an independence and imagination which promotes unusual ideas.
Perhaps I imagine things more than most, because my very first paper was returned from the referee saying you'd think she'd been out watching pterodactyls through field glasses. I always remember that comment.
Cherrie is equally at home with people and ideas.
Oh, I think it's because I act as a catalyst to people. I have an idea, you see, and I don't know what to do about it, so I find a likely-looking person and go along to him, it's always a him, and say, have you ever thought of doing so-and-so and working out so-and-so? And he says, oh no, I haven't. So I say, well, why don't you do that then? And then it all sort of happens, and I step back and it kind of all overwhelms me from then on.
She responds enthusiastically to any interesting idea.
See, we've got all these bananas.
She jumped at the proposal to build a full-scale model of Pteranodon.
Oh yes, well we often thought of making a life-size model and how nice it would be. Of course we didn't have the money.
And in thinking about it, what did you imagine would be the most important practical results of that?
Oh, I didn't ever imagine any practical results.
This was a sort of fantasy you both had?
Yes, yes. Yes.
The fantasy takes shape. It's a fiberglass replica the same size and weight as Pteranodon. Flapping is powered by an electric motor.
Well, not so bad. It obviously works. But we've still got problems. We've got that squeak to solve.
Yeah.
Probably lubrication will do that.
Yeah.
And we haven't flapped her with the membrane on, so the loads aren't right yet. And of course, we don't know what will happen when we get her in the air.
How does the flapping that you've got here compare with the flapping that the original creature was capable of?
Well, it's designed to be very much the same. We've got a motor of the same sort of power as Pteranodon's muscles, batteries which will run it for a minute or two before it overheats, and Pteranodon probably didn't flap for much more than that if you could help it either. It's interesting that to get this amount of power in, we've had to use motors and batteries which total about the same weight as Pteranodon's muscles, and the bones come out about the same weight. So we're going to end up about scale weight, scale power, so we should get the same performance.
Everything has been done to model it accurately, right down to the toenails.
Thoroughly, I think I can.
Here's a little white duck.
Nice to have a glider you can put the wrong ring on.
Oh, it's quite lovely, isn't it?
The legs are connected to the body by a universal joint so as to move up and down to give elevator control and from side to side to give rudder control. To keep weight down, the fiberglass has to be only 1 millimetre thick. Work to these specifications can only be done by experts. A local firm of glider repairers has been contracted.
Try that. No, I don't think so. It's pretty strong stuff. Has it got it?
Well, I've got wing anyway.
Building the model is already providing fresh insights into the economy of Pteranodon's structure.
The more one works on it, the more obvious it becomes that he's extremely well engineered. The materials are all put in the right places. There's material where the loads are, and there's nothing where there isn't any load. And obviously he's evolved over millions of years into a very good engineering structure.
Test day for the control systems at Lasham Airfield in Hampshire. This is the first time the model has been fully assembled. The tests are for elevation and steering, which are controlled by radio. Ex-British radio model champion Mike Birch is to operate it.
There, you see, as soon as we get the membrane full.
I think you've got some control, but very little.
Yeah.
If you look at the beak, you can definitely see the beak move.
The beak's moving in the right direction every time he moves.
Yes.
That's it, yeah.
Quite noticeable right at the tip.
If we're more or less happy and the CG is in about the right place, there's nothing more to do but go and fly her, is there?
That's about it, George.
Mike, how are you feeling now about a launch?
I think we can have a go now. We've got enough control for a hop, and that's what we're going to try now. We're going to try now.
Well, I'm optimistic. I wonder whether I can run fast enough or whether we'll have to use a car. I hope we've got enough elevator power. If we got a bit more time, I think I'd modify the controls first and fly second, but I think it's worth a try.
My point of view is if they've made it close enough to Pteranodon, it's going to work and not otherwise.
How are you feeling in yourself?
I'm terribly nervous. I've been getting worked up for days and days.
What's the bottle for?
Well, that's to celebrate when it works.
Or to drown your sorrows if it
Yes,
doesn't?
yes, but that's only a minute possibility.
The first attempt, a ground launch, is a non-starter.
Wouldn't it help if we two people, one each held
No,
the
you've
wheel?
got a communication problem then. And then you just end up with a load of pressure in the centre section.
One could do it with two people, one each spar, holding it at this sort of height.
Probably get scalped with a
The
claw.
only way to do that is to get somebody to carry the whole weight. Because then when it's ready to fly, it'll lift off. If it's not got enough...
What we ought to have, of course, is a wheel.
With all the early enthusiasm for authenticity, no one has foreseen the need for wheels.
Now, the problem as I see it is that when one tows her, she overbalances forwards. And really what one needs is a sort of projecting skid ahead to keep her upright. And what we ought to do is pack in and go away and make it, and come back and do it again tomorrow. And this has been the problem the whole time with this job. We keep finding things which ought to be done properly, and we don't do them properly. We bodge them. Now, 9 times out of 10 you can make a bodge work. The 10th time you run into trouble. And sometimes we're running into trouble.
Next, an attempt is made to see if the wings are generating lift. It's a test not just of aerodynamics, but of physical fitness.
What is going there? Pardon? Yeah, you could see the wings come up.
Yeah, they're really bent.
It was going.
Yeah.
Right.
You didn't have to hang on to hold it down.
No, I mean, like to run with it, you've got to
grip
it like that anyway.
Yeah.
Not fell.
I mean, if I could run with it.
No, you'd never get the grip. You'd never get the grip.
No. Well, it's up to you. I mean, I can sort of...
George,
Yes.
if he ran with it,
Yes.
and we towed it from the front, so he could get the initial start up, fill the cell, it'd be in the right angle of attack.
Yeah.
What do you think?
Yes, that was what you were...
And we took it from him.
And by hand or by car?
Why not?
What do you think?
Car, I think.
Shall I
Yes.
with a car? You want to go for it?
Yes, I think we might go.
It's already becoming clearer why Pteranodon was a free-soaring creature inhabiting cliff tops. Any pterodactyl raised in the flat fields of central Hampshire would presumably have evolved an undercarriage along with its paper-thin bones. Morale is low after such a hopeful start.
Did we get any lift off at the top? No.
No, we weren't going fast enough.
This is a major setback to encounter so early on in a difficult project. Even Cherrie's enthusiasm is ebbing away.
One of the unfortunate things is the launch. We didn't expect to be any problem, and it has become a problem.
Yes. We can't get her up to speed.
We can't get it up to speed. Now you see, even if if it had been windier
No
today,
wind today,
Yeah.
if it had been windier today, if it had been as windy as yesterday.
This is one place where wind is no problem. These cliffs at Rhossili in South Wales rise 200 feet above the sea. Appropriately, it's exactly the sort of place pterodactyls would choose to live.
Okay,
Ready again?
Yeah.
I'll take a little nearer the egg.
3 weeks of thought and reappraisal have passed since the failure at Lasham. A new quarter-scale model is on trial.
I don't want it to, I want it to go up.
A tail fin and rudder have been added to give stability. It's operated by radio control. The winds from the sea give superb lift as they rise over the cliffs. It's no coincidence this is a favourite place for hang gliders. These were developed from the guided parachutes which brought the space capsules into land on target. Ironically, this latest spin-off of space technology turns out to be a crude imitation of what Pteranodon had been doing for 100 million years. The wingspan of a hang glider is about the same as that of a medium-sized pterodactyl. It's also a flying wing. As every pilot knows, this poses problems of stability and steering. A hang glider solves these problems by sweeping its wing back like a paper dart and by having a brain at the controls. The model of Pteranodon has neither a brain nor swept-back wings. These will be difficult problems to overcome.
Yeah, I've got too much up on one. Okay, good. Yeah.
For Cherrie, a hang glider provides a pterodactyl's eye view of the world.
Gosh, this is fantastic! This is how Pteranodon must have felt when he took off from his cliff. Well, I just feel I've just set off from my cliff and I'm out on an early morning fly, exercising my wings, working up an appetite for breakfast.
What do you think you're going to be finding at the bottom when you get down there?
Oh, a very nice, large Cretaceous fish, which I shall promptly dive into the sea and snatch up.
Okay.
Meanwhile, George Whitfield is trying to make his model controlled and stable. The wings can't be swept back without losing their authentic shape. Instead, he's fitted a tail fin which acts like the flights of an arrow to keep the model pointing forwards. To this extent, he's happy to compromise.
I think this is real science happening under our noses. We think we're making a film, but in fact what's going on is scientific research here.
I'd rather you didn't touch him. He's a model pterodactyl. And we're making a film about him. So this is a model to see if we can make him fly properly. He's not doing too badly, is he?
What do you think of it, Cherrie?
I think it's lovely.
This is the way science really goes. There's some theory behind it, but it's mainly practice. That you try something, you see what happens. You try something else, you see what happens. But the theory guides you in the right direction.
And this is exactly what's happening here in a classical way, without people realising. The theory being our theory of how Pteranodon flew, and then the apparatus is the Pteranodon itself, the practical is the flight, the results as the feedback we're getting from Mike, Bert.
And they are, in fact, being written down.
And
you're not seeing this, but I go home in the evening and I write down what we've done. And since this is engineering, the final result will be a full-scale model that flies.
Tests with the small model provide information both about the correct angle of elevation of the legs and the dihedral angle between the wings. These will be translated faithfully to the full-scale model later.
Well, the information we're after on these particular tests is just how much fin and rudder do we have to put on the back in order to make a model of Pteranodon work. We're substituting for his brain. For example, a man can stand perfectly well on one leg, but if you take a waxwork model of a man and try to stand that up on one leg, then it falls over.
Nasty gap in one wing.
Yes.
What an airport.
Yeah.
The original plan was to build a model which combined the performance of a hang glider with a limited flapping capacity. As the final launch approaches, a look at bird flight seems logical, but has an almost wistful air about it.
Yes, the most obvious thing is the range of controls a bird has got.
Yeah.
He can move his wings up and down, forwards or backwards, twist them together or differentially. He's got a tail which he can move up or down, which he can twist and then move
also
sideways,
that's it,
which he can fold if he doesn't want it, or spread out if he wants a lot of it.
Yeah.
The brain of a bird senses any instability in its system and makes instantaneous adjustments to every flying surface. A tailplane is quite unnecessary. How could the model even approach this level of sophistication? Launch day. The wind has finally swung round from the southeast to the southwest, almost directly onto the cliff. Conditions are still not ideal. The atmosphere is hopeful, but tense.
Yeah, yeah. I want to get clear of that out.
Wait one. Can you lower this wing so I can get at it?
No, that one's just inflated. That one's just inflated.
No, but when she was up in wind.
You've got a pair of scissors, someone?
I reckon you want to right forward and right back.
How's that?
Yes. I think you're in business.
I should put 2 crosses on them.
I just give it a drop at the tip of its beak.
Yeah, I don't want it
to give it a jolly good swing, I reckon.
Cherrie's confidence at least has returned.
There you are, Pteranodon. Now do your best.
Up you go.
Yemeni Creek.
It's lifting quite well, George.
Check for controls.
If the thing's going to crash near anybody, try and grab hold of any part of it to slow its hitting the ground, without it flying straight at you. Try and duck past it and grab hold of any bit of
Going
it.
straight at you.
And that applies to all the people standing all round.
Okay.
You're okay. Right, bungee men. Walk.
Do you want some more tension on that, George?
Yes, oh yes. Keep going.
Pull on the tail, can you?
Hold back on the tail. You've got about 20 pounds.
How's that feel, John?
I should think that would go. Are you happy? Happy?
Yeah, sure.
Let go!
Lack of speed.
Yes,
Lack of speed.
lack of speed. How bad is it? What's happened up the back?
That's okay, we can repair that.
Broken
Yeah.
prospects.
Having watched that,
Yes.
I would say most definitely a hand launch. I would say there's no way that this type of wing can take that kind of launch.
You reckon it's too fast for the...
Lovely.
It was just luffed out. It luffed out, you know. I mean, that's... It was just, it just can't do it, you know.
So, a hand launch it is.
We've had a flight, certainly, yes. We had her airborne, and then she hit the launching rope. She was airborne and controlled, and behaving, in fact, just like the quarter-scale model. there was no reason why she shouldn't have gone on flying as long as necessary. This model has tried to be everything. It's tried to look exactly like Pteranodon to make a good film. It's tried to be like him in size and weight and strength to get scientific data and so on. We would probably have done better to have made 2 or 3 models, each of which was designed to answer a particular question. But we hadn't really time to do that, and I suppose to some extent we didn't think of doing that at the beginning.
Building the model was obviously instructive, the launches much less so. Was it worth all the time, money and effort?
I think it was worth a try, and it certainly might have come off. If we had perhaps another couple of weeks, I think we could get her into the air and flap. What she would do when she flapped in the air, I don't know. But we didn't know that at the beginning.
Whatever the fate of the model, the principle of applying engineering to the study of fossils has brought them to life after millions of years in an original and illuminating way. But now Cherrie and George have finished their work here. Where will they look for new ideas?
I think I'll go on with electronics. I may do something more in this field one day. Otherwise, I'm getting very interested in conservation and particularly energy supplies. And I think this really is rather more important. All the pterodactyl work is great fun, but it's a bit like fiddling while Rome's burning.
Well, the terrible thing is I agree with him. The pterodactyls is a complete escape. It's a wonderful thing to do. It's the equivalent of studying an art subject. There's no use in it. But at the same time, I feel that you've got to have this release. People have got to have this kind of escape.